Hi and welcome to this clip going through properties of alkanes. We're going to focus on shape and boiling points only. So if we take bond angles and shapes first of all, we can see how they apply in some organic compounds. So if we have a look at a simple example like ethane, you can see there's 4 bond pairs and no lone pairs around each carbon atom, and because electron pairs repel, that causes the molecule to adopt a tetrahedral shape with 109.5 degrees around those carbon atoms. If we were to go and look at another example, this time with a carbon-carbon double bond, I've chosen this one so we have 2 separate bond angles going on in different places. So the carbon-carbon double bond counts as 1 bond pair when we talk about shape. So that means there's 3 bond pairs and no lone pairs around that carbon, and that would give it 120 degrees, which is reflected in the way that the structure has been drawn. So again, we've got 4 bond pairs and no lone pairs on the end carbon there. So like before, that's tetrahedral and 109.5, and that means that there's 2 different shapes and 2 different bond angles going on in different locations in this molecule. So let's now look at the boiling point in alkanes and what affects it. So if I move myself up here, the relationship we want to focus on is the connection between chain length, or molecular size, and the surface contact points over which London forces can occur. So London forces are the only intermolecular force that are going on here because you have got only non-polar bonds. So if we were to look at the idea of surface contact points and draw a circle around butane, you can see that it's a slightly bigger molecule than methane, and there's slightly more surface area over which London forces can occur. Obviously that effect is increased further at hexane and octane, and you can see for yourself the data suggests that the boiling points steadily increase. So if we look at this little animation, which just shows how London forces arise again, the electrons are randomly distributed in nonpolar molecules, and if they happen to drift into a position where a dipole is induced, that can cause an attraction between the molecules and they move together. And then if the electrons move back to the original positions, that will cause the dipole to disperse and the force will stop working. So this is the only intermolecular force present in alkanes, and therefore the more surface contact points that are present in a molecule, the greater the number of London forces that can arise simultaneously. If we look at it in octane, you can see that there's quite a few London forces that could arise at the same time, and if the molecules are orientated so that the long ends of them are butted up together, so there's a lot of surface contact points available, what will happen is those London forces will cause a significant amount of attraction between those 2 molecules, hence why the boiling point of octane is 128 degrees and the boiling point of methane was, I think it was around at minus 164 if I remember correctly. So if we look at the isomers of butane and explore this a little bit further, if we build up the butane molecule from the carbon chain, and we've got its isomer on the right hand side, 2-methyl propane. I'm just doing it this way so you can see it's important to make sure all the bonds are actually included when you're actually drawing these out. So these are the fully displayed formula now, showing all the bonds and all the atoms. And if we look at the names, we've got butane and 2-methyl propane. And the butane is a straight chain hydrocarbon, the 2-methyl propane will be a branched hydrocarbon. And this actually gives significant differences in physical properties. So the melting point of butane is minus 138 degrees C, but for 2-methyl propane we've got minus 159. For boiling points, we've also got a significant difference. So you can see a lot less energy is needed to overcome the London forces in 2-methyl propane. That's because it has less surface contact points for London forces to arise. So if we were going to go and look at graphing this data, that gives us a fairly sort of linear relationship, and you can see methyl propane just below butane at the top bucks that trend, doesn't it? So therefore that's because methyl propane is branched and there's lower surface area, so less points of surface contact for London forces to arise. If we were to look at it for C5H10, a similar situation occurs. Again, decreasing boiling point, less surface contact points for London forces. Okay, thanks for listening. Hope this has been useful. Until next time, see you soon.